Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe what the electron volt is, or what's usually just called the EV. So before we talk about the EV here, I want to chat about the four objects I have shown here. So I've got this picture of an aspirin, this young little lad here who likes to play basketball, a car, and the car's not moving, by the way, don't worry, he's not going to get ran over, and a building. And right now, before I begin with the video, I'd like to, anybody watching this, ask the following question. Take a moment, and if you had to assign a weight to each of these objects, think about what those numbers would be. So go ahead and maybe pause the video, think about that, come up with a number for each object. Okay, so hopefully you've done that little exercise here. And, I'm going to kind of go through these kind of one at a time. So, let's talk about the aspirin. Aspirin's a tiny, tiny little thing. When we take aspirin, we usually are, dosed by the, or given a number that, typically would be measured maybe in the milligram range, or another appropriate unit of weight would be the grain, right? A grain is a very small unit of weight. In fact, I think there's 7,000 grains in 1 pound. Now, usually things like aspirin actually have a gram or milligram weighting on them. This is not technically a unit of weight. This is a unit of mass. The grain actually is a unit of weight. Not important for the discussion. I just want to be sure it's clear that the gram isn't. It's a unit of mass and not weight. And if you're not clear about what that means, I've got videos on the differences between weight and mass, and please go back and review them. For now, let me just use the term grain here. So this aspirin might be 20 grains or something like that. Right, the young lad here, this is a young kid. He might be, maybe something like 60 pounds or 70 pounds or something like that. An automobile. Well, the weight of the automobile, maybe just kind of throwing a number out there, maybe something like 3,000 pounds. That's just a guess. Or, somebody might say maybe ton and a half, something like that. But the most likely scenario here is somebody would give you a measurement in pounds. All right, and here we're looking at a building. All right, what would the weight of the building be? I don't know. I have completely no idea. I'm just going to throw a number out there. This building might be, 20,000 tons or something. The important thing I'd like to point out is when asked questions like this, no one would try to give you the weight of this building in grains or grams. And over on the left-hand side, nobody would give you the weight of an aspirin in tons, or probably not even pounds. All right, and the weight of the child, very few of you probably said, oh, the weight of that child is so many grains or so many tons. All right, so the grain, the pound, the ton, these are all units of force in the English engineering system. They all measure force. However, you don't, where you use which, you use them according to appropriateness. No reasonable person would give you the weight of that child in tons, or the weight of this aspirin in tons. And furthermore, nobody would probably think to give the weight of this building in grains. You use whatever unit is appropriate. So when we get down to the scale of the atom, all right, I'm going to draw a quick model of a hydrogen atom, just really quick. So a hydrogen atom here, we've got a positively charged nucleus, and then we've got an electron out here, right, that's going round and round. Now, again, every time I draw a scale of an atom, I have to mention this is not to scale. If the proton were actually this big, you couldn't see an electron. Or maybe if I took some ink and used a pin and kind of dotted that pin and hit the screen somewhere, it might look something like that. And also, if the proton were this size, this orbital distance here would be many thousands of times larger. I mean, way, way, way larger. And again, if you're wondering what I'm talking about, go back and review my video about atomic structure and relative sizes of the orbits compared to the nuclei. But the big thing is this, this electron has a certain energy, which is the sum of two things. It's potential energy plus kinetic energy. And remember that the electron's mass is 9.11 times 10 to the minus 31st kilograms, right? So the kinetic energy here, if I take a look at a kinetic energy term, 1/2 mv squared, and you'll notice this is almost 10. This value is approximately 10 to the negative 30th. And even if this electron were moving at, say, 10 to the 6th, or I'll even do 10 to the 7th power, and that's being squared. And we take a look at this product here, 10 to the negative 30th times 10 to the 7th squared. This is 10 to the negative 30th times 10 to the 14th power. And this ends up being, 10 to the negative 16th power, right? Even this is a relatively large number in the world of electrons. When you're talking about the energy of an electron, typical energies are come out to about 10 to the negative 18th, or maybe 10 to the negative 17th power. So for this reason, remember the energy units here. If this is in kilograms and this is in meter per second, then this would be in kilogram meter squared per second squared, which is a joule. So when you measure the energy of an electron in an atom, 10 to the negative 18th power is very common. It's a very common number in joules for electrons. And for that reason, the joule is not a very convenient unit to measure electron energies in. So electron energies are measured by what's called the electron volt. And an electron volt is defined as the energy of an electron accelerated through a potential difference I'll just put a delta V here, potential difference of 1 volt. Okay. So you notice that the term voltage is kind of important here. Remember, electric potential is defined as potential energy per unit charge. So potential energy is equal to charge times potential. So you notice charge times potential is an energy. If we take the charge of an electron, which is 1.6 times 10 to the minus 19th coulombs, and then multiply by a 1 volt potential difference, and remember a volt is a joule per coulomb, so 1 joule per coulomb, what we get is a numerical value of 1.6 times 10 to the minus 19th joules. This energy is equivalent to 1 electron volt. So I'll just summarize this real quick. An electron volt, or an EV, is a unit of energy. It's a unit of energy that's appropriately scaled to dealing with electrons. And 1 EV is equal to 1.6 times 10 to the minus 19th joules. This is the conversion factor for going back and forth between joules and EVs. So I hope this video cleared up or allows you to understand what an EV is and why it's used. Again, it's just a unit of energy. It's numerically the same as the charge of an electron because how it's defined. Again, energy of an electron accelerated through, I know it's a little hard to read there, a delta V of 1 volt. So, hope this video helps. Have a great day.